So today we're looking at the brief for straight and level. So since this is an online brief, I'll skip over housekeeping. So aim. To understand techniques to accurately fly the PA-28 in straight and level flight at various power settings. So the different configurations we'll be using to fly the airplane, recognizing the appropriate flight attitudes. So the attitudes we need to adopt to fly the airplane straight level, and ensuring the airplane is always in balance. So that's to do with the airmanship of this lesson, to make sure the airplane is in balance and trimmed for straight level flight. Motivation introduces the fundamentals of controlling an airplane in the cruise configuration. So we'll have a look at different various types of cruise configurations, such as fast cruise, slow cruise, safe slow cruise, and normal cruise as well. 90% of your flying will be in the straight level configuration, so it's really important that you're proficient in this maneuver. And it's the first step to becoming an accomplished aviator as well. So we'll set the building blocks for other maneuvers such as climbing, descending, and turning. So an overview of what we'll have a look at. So objectives, that's the take-home message. We'll have a look at our revision from our effects control brief. We'll look at the definitions that are relevant for today. We'll have a look at the 4 forces that go on our airplane in straight level flight. We'll have a look at Bernoulli's theory, so that's another theory to tell us how lift is produced. We'll look at the engineer's lift formula, which we briefly touched on in effects control, and then from then on we'll further look at the pilot's lift formula, so things we can control as pilots. We'll look at the power curve, then we'll have a look at power and thrust, and then we'll have a look at stability, so know the different types of stability an airplane can demonstrate. We'll look at the application of what we'll actually do in the air. The airmanship and threat management considerations, so some of the threats that exist in the lesson and how we can mitigate the risks. I'll summarise everything, and then finally I'll ask you a few questions with the objectives. So following this brief, you'll be able to, from memory, name the forces that act on an airplane in straight level flight. So it's important, as pilots, we want to know what the forces are doing to our airplane in flight. Name and describe the 2 ways an aerofoil produces lift. So we've already looked at one theory, now we want to have a look at another theory that lets us know how lift is produced. State the methods a pilot can use to vary the production of lift. So we'll have a look at things that are in control for us as pilots and things that aren't in control. Describe the 2 main types of drag. So we'll have a look at drag at both slow speeds and fast speeds. And then finally describe different configurations for the PA-28 in straight level flight. So this is important, forms the basis for our air exercise. So revision. Name one theory that tells us how our airplane generates lift. So I'll just give you a moment. If you want, you can pause the video and you can come up with these questions. So we looked at the flat plate theory, and that's important. Now we'll have a look at the Bernoulli's theory, which is another theory. Name 2 factors that affect the production of lift. So 2 are airspeed and angle of attack. Other factors are surface area and density, and we'll have a look at that. How we'll look at things that are in control of the pilot and things that aren't in control. What are the 3 axes of motion? So we've got pitch, roll, and yaw. This is important. We have 3 control surfaces on our airplane, which allows us to move around these 3 axes. And then name one ancillary control, its effect and limitation. So an ancillary control is the mixture control. Controls the amount of fuel that is going to the engine. And limitation is you must lean it on the ground for ground operations. So in terms of definition, so airfoil/wing is a shaped structure capable of producing lift as it passes through the air. So an airfoil is pretty much the cross-section of our wings of a GA aeroplane, and we like to say it's a cambered wing. It has a lot of camber, and we'll go over what camber means as well. Mean camber, the line joining the leading edge and trailing edge halfway between the upper and lower surface. So pretty much tells us the curvature of the wing. And this line, this dotted line, as you can see, it's equidistant between the top part and lower part. And then camber, the curvature of the airfoil is measured at the maximum distance between the mean camber and the chord line. So that's this line over here, camber, and also tells us, about the how curved it is from the chord and the mean camber. So we've got 2 airplanes over here. So a cargo airplane needs a lot more camber than a glider because it needs to carry quite heavy loads, whereas a glider doesn't need as much camber. Sure, it does have a little bit of camber, but not as much as a heavy cargo aeroplane. So inertia, an object's ability to resist a change in motion, i.e. an object in motion will stay in motion unless acted upon by an unbalanced force, and the same principle applies to an object at rest. So for example, these marbles, when they come to a stop, they suddenly want to go forward as they're used to moving, and this coin over here, when you remove the cardboard, it wants to stay still, so it sinks to the bottom. It doesn't move along with the piece of paper. It's kind of like, being in a bus. When a bus driver suddenly brakes, you feel yourself flinging forward. That's due to the inertia. And the more heavier the object, the greater the inertia as well. Center pressure, the point at which lift acts through. So simply put, lift really acts through the whole surface of our wing. But we like to summarize it, keep it simple. So we say that it's a summary of all the forces acting along that point of the wing. So what is straight level flight? So it's about holding a constant heading. So that's a straight part, holding constant altitude. So that's the level part. Having a constant speed and making sure you're trimmed and balanced as well. So with a constant speed, you're not either accelerating or decelerating the airplane. So all the forces, as you'll show in a moment, are in equilibrium. So this is what we'll see in the training area. We'll have to adopt an attitude. So for example, once the ground to the sky, and providing the power is set and the attitude is set and we're trimmed, we will be in straight level flight. In this lesson, we've got the threat of weather, operating the training area out of Bankstown. The area will be not monitoring your TAF or ATIS, so make sure to maintain visual conditions, otherwise it could lead to non-visual flight. So that's really important that you check the weather. So lift is the force that holds the airplane in the air. It acts perpendicular to the relative airflow. So we've got the four forces with lift. We will look at the flat plate theory that tells us how lift is produced, and then we'll have a look at Bernoulli's theory. And then weight, the force acting vertically by pulling the airplane towards the center of gravity. And we'll also look at how weight is calculated, what weight is. Thrust is generated by the propeller and acts along the propeller shaft. It moves the airplane forward, so it's really important. We need enough thrust so that we can have airflow over the wings to produce lift. And a drag is a mechanical force that is generated by the interaction of the airplane with the airflow, and it pretty much wants to slow the airplane down. So lift and Bernoulli's theory. So our atmosphere is comprised of air molecules which are either still or moving. So it's either one of those things. And total energy in a fluid remains constant. So total pressure equals static plus dynamic pressure. So they're both inversely proportional. And static pressure acts on us all the time. So we don't feel it, but it does act on us. And dynamic pressure is the movement of air. If you move your hand around, that same static pressure now transforms into dynamic pressure. And that's why total pressure equals static plus dynamic. It is either static or dynamic. So now I'm going to explain Bernoulli's theory. So first off, we've got the shape of our aerofoil down over here, and it can be thought, and if we've got Bernoulli's Venturi, something he designed, and it can be thought as the shape of an aerofoil. So the airflow has to at the starting of the wing has to meet at the same point at the end of the wing. But we've got a greater distance over here, so therefore the air on the top part of the wing has to travel faster than the air below the wing. It's kind of like with a river. If the river got a constant speed, but when there's a narrow section, the water speeds up to get through that narrow part, and then it returns back to its normal speed. So pretty much when you're over here, dynamic and static pressure are equal, but then over here, that air, as it goes faster around the surface, the static pressure decreases, but that dynamic pressure increases. That static air now transforms into dynamic pressure, and then when it returns to the end part, it returns to normal pressure. So there's a low pressure sort of system here, pressure decreases, and pressure stays the same here, but we like to say higher pressure as well, and that's what creates lift. And if you blow across a piece of paper, the thin piece of paper across the sides, you'll notice that that will cause the paper to fly, so that will cause a lift as well. So engineers lift formula. So created by engineers to explain the mathematical interpretation of how lift is produced. And we also related this to the flat plate theory in terms of the 4 factors. So we've got angle of attack and wing shape, so camber. And the reason why coefficient of lift is determined by camber, because camber can also affect our angle of attack. Then we've got half rho, which is air density. So the rho is a Greek letter in their alphabet. Then we've got v squared. So it's the reason why it's squared is because speed has a greater effect in terms of lift. So that's why we need to square it. And then S is for surface area. So if you cross out all the variables from the engineer's formula in terms of things we can control angle attack using our control column. Can't really control wing shape. Yeah, sure we can using flaps, but not really for straight level fly. Air density you can't control. You can control speed using your throttle, and we can't control wing surface area. An interesting point is this actually gives us airspeed. So half rho v squared is air density and speed. So that's what our aeroplane's pitot tube, that's what it measures as airspeed. So from a pilot's view, we can only control angle of attack and speed. So power plus attitude equals performance. So we as pilots can only control airspeed and angle of attack. So by setting the power and the attitude, we will get our desired performance of a straight level flight. So that's our desired performance of having a level altitude and a straight heading. So, and this is only for a constant weight and holding a constant altitude, as weight can, weight can change the amount of lift we need. So if we have low indicated airspeed, we need to compensate by having high angle of attack. And if we didn't have high angle of attack, we wouldn't maintain level flight. And if we had high indicated airspeed, we need low angle of attack. If our airspeed was too high, we'd start to climb. So they're inversely proportional as well. And the angle of attack, as I mentioned, is set by the attitude, and the indicated airspeed is controlled by the throttle. And that's what you'll see in straight level flight. We're not changing our lift, we're just changing where it's coming from. So in terms of the training area, what we'll do is set the power and set the attitude, and if we're trimmed, we will get straight level flight. Weight. So total weight is a single force acting through the center of gravity. And it always acts towards the center of the Earth. So it acts towards the center of gravity towards the center of the Earth. Weight equals mass times gravity, so that's how it's determined. Mass is the physical substance of an object, the physical amount of matter, and in balanced flight, lift and weight are equal. So you can also reimagine this formula like this. So drag, total drag equals induced drag and parasite drag. So remember, we looked at this in our objectives, how drag affects the aeroplane at both fast and slow speeds. So total drag, it's the same drag, but it's split into induced or parasite. So induced drag is a byproduct of lift. So when you have, the reason why induced drag starts off high and then decreases is because at slow speeds you've got quite high angles of attack, which is quite unaerodynamic. And parasite drag is caused by moving a solid through a fluid medium. And there are 3 types of parasite drag: form drag / profile drag, skin friction, and interference. And the reason why it starts off low but increases as we get faster is because all the air has to move out. It has to move out quite quickly, and remember that air causes the drag. So induced drag is a byproduct of lift. So as a consequence of producing lift through high angles of attack, is a result of low airspeeds and high angle attack, i.e. during takeoff and landing. So that's when we have to fly. That's why when we fly the airplane slowest, as we need to accelerate to cruise speed, or we need to slow down and prepare the airplane for landing. And you've also got trailing edge vortices, so as you can see in this image. It is caused by the spillover of high pressure air underneath the wing moving to the low pressure above the wing. So high pressure always moves low pressure. So as that difference comes over here, it sort of has a spillover effect. Wingtip vortices occurs the same way, but moves clockwise or anti-clockwise. So over here on the left wing, the high pressure wants to feed that low pressure, so it moves in a sort of clockwise direction, and on the right wing, the high pressure moves to low pressure, and it moves in an anti-clockwise direction. So we can't really normally see the wingtip vortices, but if there's enough moisture in the air, you can see it as well, and that's that induced drag. So form drag caused by air having to move out of the way as the aeroplane travels forward, and is minimized by streamlining. So pretty much the easier you can make it for the air to move out of the way, the more streamlined it is. So we've got a flat plate here, one of the most unaerodynamic things, but when you have a sphere, it becomes a lot more aerodynamic. A sphere with a fairing at the back allows the air to smoothly join, and then finally a sphere inside a housing as well is most aerodynamic. It's one of the most aerodynamic objects. It's an over 90% reduction in drag from that same flat plate, and now that it's inside a housing. And it kind of also looks like our image of our aerofoil. So in terms of these two airplanes, so the Concorde has a lot less form drag than this airplane over here, because it has to fly at quite fast speeds, so it needs to make sure it's minimized and streamlined as well. Whereas this airplane doesn't fly as fast as Concorde, so it doesn't need to worry about form drag as much. So I've got screen friction. So aerodynamic resistance caused by air sticking to the surface of the airplane. So that's the definition. So rough surfaces can also cause the airflow to stop smoothly. So it can be minimized by ensuring the air surface of the airplane is clean. So over here, smooth surface is less friction, but a rough surface, the air stops flowing smoothly and also gets caught up over here in terms of the edges. So if you slide your hand over carpet versus a smooth timber floor, there's more skin friction on that carpet. So here we've got two airplane wings. We've got the airplane on the left, and we've got a cirrus wing, so it has less skin friction than the Cherokee wing, which has a little bit of nuts and bolts. It's got that fuel cap as well hanging on top. So finally, parasite drag interference, so caused when two moving airflows meet from different directions or at an angle. An example is the airflow over the wing compared to the fuselage. So they're both flowing against different surfaces in a different direction, and it's kind of like a river as well. If you've got a river flowing from two different directions, and then when they join together, they have a sort of swirling motion, and then as they continue along and join. So it can be minimized by smoothing out corners, as also make it, as you can see in this image, by using fairings as well on the wheels. So drag curve, so by applying the induced drag and parasite drag, we can see the point where the total drag is a minimum. So you've got the induced drag here and the parasite drag curve, and by getting the total drag, we get that U-shaped curve. And this is known as the minimum drag speed. So more of this in our descending brief. This is the speed for minimum drag. So what happens is if you glide at this speed, you will encounter minimum drag, so you have a lot more range. You'll get the best range if you had an engine fan. So thrust is the result of all the forces produced by the propeller that move the aeroplane forward. And thrust is highest at low speed and decreases as the forward speed increases. So the reason being is, it's kind of like when you're canoeing. When you're starting out, you've got a lot of grunt, a lot of force available to canoe the airplane. And then it gets to a point where no matter how much you're going fast, where no matter how much you canoe the airplane and paddle, you can't go any more faster. It's kind of like the propeller of our airplane. Starting out on the runway, you've got all this force, all this grunt available in terms of your propeller, which can push a lot of air back. But when you get to a point where no matter how much the propeller spins faster, for example, straight level flight, the amount of air it pushes back matches its forward speed. So that's why it increases and then decreases. Thrust required is simply to overcome that total drag. So that's why it's in that U curve. So power is the rate of doing work, so into revolutions per minute. So when you see that word rate, it's to do with the unit of time, so we're talking about revolutions per minute. So the engine produces power controlled by the throttle, while the propeller produces thrust. So that's the key difference. And that formula over here to get power equals thrust times speed. So horsepower available, that's available for our engine. So when we're starting out slow, power equals thrust times airspeed, slow airspeed, not as much power. But then it flatlines as you get faster and faster, as your airspeed is fast, and your thrust is a lot as well, so you get a lot more power. And then horsepower required, that's the horsepower required to fly at that specific airspeed. And the reason why it starts off high and goes low is due to that inertia. Due to the weight of the airplane, we have to overcome the inertia, and that takes a little bit of time as well. And as well, the threat of engine damage in this lesson, the aero will be using a high power setting. So make sure you monitor the RPM, otherwise you will exceed that red line, which was 2,700 RPM for aeroplane. So make sure you monitor that. So now we'll look at stability. So stability is the natural tendency of the aeroplane to return to its original attitude following a disturbance. And maneuverability is the aeroplane's ability to deviate away from its flight path. So stability and maneuverability share an inverse relationship. So pretty much in maneuverability, it doesn't want to stay where it is, but in stability, an airplane wants to stay where it is. So our airplane's Cherokee is quite stable. It wants to remain in straight level flight, whereas a F-18, a fighter jet, is quite maneuverable. It's meant to be maneuverable and isn't very good at straight level flight, but is able to do so using the help of computers. So stability, there are two types of stability an airplane can demonstrate. So static stability, the tendency of the airplane to return to its original attitude following a disturbance, and then dynamic stability, returning the airplane to dampen out oscillations. So it can either be positive, neutral, or negative stable, and I'll show you as well what it looks like in terms of our airplane. So positive returns to its original attitude. Neutral remains in that disturbed attitude, and negative stability deviates further and further away from its attitude. So positive static stability, an airplane will return to its original attitude after a disturbance. So disturbance could be from an atmospheric disturbance, a wind gust, or turbulence, but providing the airplane is trimmed. Neutral stability, an airplane will remain in its disturbed attitude. So if you're not trimming the airplane properly, it will continue remaining disturbed. And negative stability, an airplane will deviate further and further after being disturbed. So unless the pilot applies a control input. And for aeroplanes, for straight level flight, we want that positive static stability. So positive dynamic stability. So if you look at through oscillations, remember dynamic relates to movement. The oscillations will decrease over time. And our airplane does demonstrate positive dynamic stability, and I'll show you that in the training area in flight. Neutral stability, so the oscillations will dampen out and remain constant. So it will sort of remain in that oscillated state. And then finally, with negative dynamic stability, the oscillations will increase over time. So unless the pilot applies further input, the oscillations will only get worse. Stability designed around the lateral axis, longitudinal, and normal axis. So lateral axis, we call it longitudinal stability. So reason being is the lateral axis, you pitch your nose up and down. So that sort of goes in between that longitudinal axis, that straight line. And then longitudinal axis, we call that lateral stability. So as we roll the airplane, that goes to that straight line of the longitudinal, the lateral axis. So longitudinal stability. So the angle of incidence on the main plane, 4 degrees, is greater than the tail plane. So there's a greater proportional increase of lift on the tail compared to the wing. So when the pilot pitches his nose up, say by 2 degrees, on the wing, it is a 50% increase in lift. However, in the stabilizer, there's a 100% increase. So this will cause the tail to rise, lowering the nose of the airplane. And you'll see this in flight in terms of longitudinal stability. I'll demonstrate this. So what will happen is I will have a low nose attitude, and we're going to increase our speed a bit, which will increase our lift in our wings. It's going to pitch our nose up, and as our nose pitches up, the effect of lift on the main plane, in the tail plane is greater than the main plane, which will lower the nose and it will oscillate back and forth until we're back into trim position as well. So we'll see this in flight. Lateral stability, a plane with high lateral stability return to a wings level attitude after rolling. So let's say the airplane rolls. On the dihedral wing, so that's the shape over here when it goes at an upwards angle from the fuselage. The low wing will have a greater angle of attack to the sideways airflow than the high wing. So we've got a high angle attack over here on the lower wing and the upper wing, which will cause more lift and return the airplane to wings level. Due to that, and you can see this in the engine lift formula, more angle attack means more lift. So lateral stability and pendulum effect. So on a high wing airplane, e.g. a Cessna, it has a less dihedral effect than a Piper Cherokee, but it still has a good amount of lateral stability, and that's due to the pendulum effect. On a high wing airplane, the center of gravity is below the wings, and when the airplane rolls, the force of gravity causes the weight to act downwards, making it roll wings level. So as you can see, the airplane's rolled. Force of gravity wants to have that restoring force to roll at wings level. It's kind of like a pendulum as well. And directional stability, so this is stability around the normal axis. So this is Newton's third law. Every action has an equal and opposite reaction. So when the airplane yaws, the tailplane will experience the relative airflow pushing against the tailplane. So the airplane is yawed, that relative airflow deflects off that tailplane, and every action equals equal opposite reaction, which wants to return it to its wing normal position. This will cause the tailplane to return to the original position. And we'll see this in the training area. So it's kind of like a dart or a feather, which has got that tail section. It allows it to have act as to provide the airplane with extra bit of stability. So we'll see this directional stability in the training area. So in terms of the application, so we're going to do a pre-entry checks. So we're going to select a reference point. Because we've got the threat of a poor reference point, the air will be losing your reference point, and the undesired aircraft state will be disorientation. So make sure you choose a good prominent reference point. You're going to put your carb heat as required. So we need carb heat below 2000 RPM. So there is one configuration we'll need it for. Mixture fully rich, T's and P's in the green, and look out clear right, clear center, clear left. And as an added safety, look above. So an easy way to imagine this is you're looking at inside, looking outside, then you're going from right to left, carb mixture, T's and P's, and then you're looking outside to clear the airspace. So entry is done using power, altitude, speed, trim. So power we set using our tachometer over here, or the RPM. Get the tachometer over here. You can set the RPM, and whenever you change power, you have to do something with your feet. So remember, when you're increasing power, you increase the slipstream effect. So you need to apply a little bit of right rudder. Decreasing power, you need to apply a little bit of left. Attitude, whether it be 1/3 ground, 2/3 sky, nose on the horizon attitude, and I'll show you as well in flight. I'll describe how many fingers are you holding in between the dash of the airplane, which is this top section, and the horizon. Speed, you want your speed to be stabilized. We may or may not get that speed, but it will depend on the in-flight conditions such as air density and temperature. And then you're trimmed as required as well. So in terms of our configurations, so we've got normal cruise, so I'll explain why. So that's done at 2400 RPM, attitude 1/3 ground to the sky, so speed 105 knots, and you're trimmed and balanced. So fast cruise, so you apply at 2500 RPM, slightly lower than normal cruise, and speed 110 knots, and you're trimmed and balanced. Remember, you've got a faster power setting, so a little bit of right rudder, and attitude, remember you need to lower the nose. Remember, with the pilot's lift formula, you've got a lot more lift coming from indicated airspeed, so you need to lower that attitude, and you get a faster speed, 110 knots. Slow cruise, so make sure to apply that carb heat on for all power settings below 2000 RPM. So carb heat in your pre-entry checks, and then 1900 RPM. Attitude, nose on horizon, speed 75 knots, and you're trimmed and balanced. So you'll have a high nose attitude, because we've got a low power setting, we need to compensate by increasing our angle attack. Say slow cruise, so 2100 RPM, 3rd ground plus 2 stages of flap. So the airspeed must be the white arc range before extending flap. So that's one of the threats as well, not verbalizing white arc. Error could be airframe damage. Error could be flap extension above VFE, and a desired aircraft state is airframe damage. So make sure you verbalize white arc. Speed is 70 knots, and then you're trimmed and balanced. And what you'll see is a good forward view due to the flaps, but you're going at a slow speed, which is due to that drag on the flaps. But it allows us to slow down as well, maybe for traffic separation. So normal cruise, it's the most common cruise. We use it on long legs if you're doing navs. Fast cruise, if there's a medical emergency, we need to get somewhere quick, we can use fast cruise. Slow cruise, the engine, we've got high T's and P's, we can allow the engine to catch its breath and apply a bit of a low power setting. Safe slow cruise, due to that traffic separation as I mentioned as well. So work cycle is done using ALAP, so attitude, lookout, attitude, performance. So during slow level, we must monitor our attitude and performance, and we must also keep a good lookout because the training area is quite a busy airspace. So we've got that threat of traffic. The area we'll be using not doing your ALAP cycle. The undesired aircraft state will be an air proximity event, so make sure you manage that as well. So 80% outside, 20% inside ratio. The ALAP cycle ensures that we check these factors in the correct proportion. So let's say we're doing normal cruise, so attitude, third ground, two-thirds sky. Lookout, clear right, clear centre, clear left. Attitude, third ground, two-thirds sky. Performance, we've got sufficient speed, we're maintaining height, VSI 0, maintain direction, turn slip, corner, wings level, and balance in the middle. And I'll show you ALAP, that's one of the first things in flight. So it's really important you maintain and do your ALAP cycle so that you can maintain a straight level. And adjustment is done using CCHAT. So you don't really say CCHAT out loud, it's more of a subconscious thing. So if you find any deviation due to in straight level flight during your ALAP cycle, use CCHAT. The correction cycle will ensure that you adjust the appropriate flight attitude. So let's say you're not at third ground, two-thirds sky, so change it. Check your attitude that is in the correct attitude. Hold it to see if it is being maintained. Maybe you check your instruments as well. You're maintaining height, maintaining direction. Adjust your attitude and then trim as required. And you may even need to adjust your power setting to correct it. So application. So first off, we start our pre-entry checks. So reference point selected. So for the normal cruise, carb off, mixture fluid, T's and P's agree. Do a good thorough lookout. Entry is done using pass. So 2400 RPM. Attitude 1/3 ground, 2/3 sky. Speed 105 knots approximately for the Warrior, and you're trimmed. Maintenance, attitude, lookout, attitude, performance, and the control is doing change, check, hold, adjust, trim. So it's really important, maintain that ALAP to successfully maintain the maneuver. And then every time we exit, if you're in the fast cruise or slow cruise, back into the normal cruise. So you're doing your pre-entry checks again, and back to the normal cruise. So Airmanship, using handing over, taking over procedure. So that's extremely important, which we've been doing very well. Which we, we need to do it well since we're operating in the training area. And I have control. It's always the last thing that's said. Actively listening to traffic instructions to tower to ground. So it builds a mental picture as well of what the traffic is doing in the training area or coming over in and out of Bankstown. Utilising cockpit to identify that traffic, and so we rely on that see and avoid principle, so we can see the traffic and avoid it. Smooth control inputs in terms of the throttle, flaps, and the control column makes it a lot more comfortable to fly. Trim the airplane and engine and fuel control. So you're not monitoring just your T's and P's. So that's really important that you look for ammeter, the suction gauge, pardon me, and circuit breakers. Maybe if they've popped out, that's the things you're looking for. So in terms of threat management, so we've already gone through this exercise, so it's just a brief brush over. So threat of traffic, every eyes inside the cockpit or poor lookout. Management eyes outside the cockpit and the cockpit code, and the undesired aircraft state with air proximity event. So make sure you watch out for that. And then we've got a certain threat. The area will be not checking status. Management technique will maintain VFC, maintain situational awareness, and the undesired aircraft state will be non-VFC flight. So that means visual meteorological conditions. So a flight where there's good weather for visual conditions. You can see the horizon, and you're clear of cloud, and the threat would be weather. So that's really important. Engine damage, power too high, and desired aircraft state with exceeding red line can cause engine overheat or damage. So make sure you monitor RPM and you do your ALAP cycle. Threat of high speeds, extending flap above VFE. Check power setting, check white arc, and the undesired aircraft state will be airframe damage. So that's really important. You verbalise that white arc as well. And these are 4 threats. Certainly not limited to these 4. There's certainly a lot more threats that exist. So make sure you're aware and you're safe in flight. So in terms of the summary, we looked at the revision from our effective control lesson. Looked at definitions that are relevant for today. We looked at the 4 forces in flight, so I'll be asking you questions. We looked at the Bernoulli theory and Bernoulli's Venturi. We revisited the engineer's lift formula, and we looked at how we got the pilot's lift formula. We looked at power curve, power and thrust curve, and then we moved on to stability, so looking at positive, neutral, and negative stability in terms of static and dynamic stability. The application, make sure you know those configurations, those 4 configurations well for straight level flight. Airmanship, threat and emergency considerations, make sure you watch out for traffic, watch out for weather, and you extend that flap below the white arc range, at or below, and you monitor that power setting so you don't redline. And then finally with the objectives. So I'll give you a moment, you can pause the video, and then I'll read out the answers. So from memory, name the 4 forces that act on an aeroplane in straight level flight. So I've got thrust, lift, weight, and drag. Name and describe the 2 ways an aerofoil produces lift, so the flat plate theory and Bernoulli's theory. State the methods a pilot can use to vary the production of lift. So we've got that power plus attitude, and that's what we use to get the desired performance, or that which is lift. Describe the 2 main types of drag, so we've got induced drag and parasite drag, and describe the fast configuration for the Warrior in straight level flight. So 2500 RPM, attitude 1/3 ground, slightly lower than 1/3 ground to the sky, speed about 110 knots, and your trim and balance. So thank you all so much for watching, and I'll see you in the next brief.